do a demonstration where I convince you that simple harmonic motion and uniform circular motion are the same darn thing, but only if you're looking at the uniform circular motion from the point of view of one component. When you look at uniform circular motion from the point of view of one component, then you should see that simple harmonic motion and uniform circular motion are the same thing. After I've done that, then I'm going to define what amplitude is, and then talk about a relationship between the position of my spring mass system and the the vertical position of my uniform circular motion thingy. Then we're going to define frequency, angular frequency, and period. And then finally, we're going to revisit this and talk about maximum velocity and maximum acceleration of a spring mass system. Okay? But the weird thing is, the thing that I'm going to have to ask you to change your brain on is this idea that you're going to see up and down motion and picture it in the context of circular motion. So you'll be able to talk about this having an angular frequency in radians per second, even though it's only moving up and down. And I'll be able to talk about, well, this mass and this thing here, wait a second, these two guys are 180 degrees. Gosh, I'm 180 degrees out of phase. And you go, how can you talk about angles 180 degrees out of phase? There's no angle there, there's no rotation. Well, I'm going to hopefully convince you that you can start thinking of things in that way. So first, let me set up my swell little demo. Now it doesn't work out perfectly, but it works out good enough. And good enough is going to have to be good enough. So there's my thing there. So, are you guys able to see that uniform circular motion thing happening? Can I get it? Can I get it closer? It's kind of gotten a little kilter. All right. There we go. So here's my circle. And so what I'm hoping to show you is that, look at this paper that I've taped in my circle. And so if you see this guy going up and down and see that paper, if you just looked at the y coordinate of the paper, you'd see that the paper is kind of matching. Wait, come on. It's kind of matching that, but that's not very easy to see. So what it's easier to do is actually to turn this wheel 90 degrees and then put it here. And so do you see that paper going up and down? Now just look at the shadow of the paper. What the heck? Oh, I see. It's always hitting that thing. Here, just a second. Here, let me bend this a little bit. And do I have my tape? Let me get my tape. Just a second. So that the cameras just roll in, and that's okay. Here, this stuff.
Hey, you did general.
So, all right. So, if you see that, oh, it's not that obvious now, is it? That's why I needed it to be out there. I want to tell the video audience that this actually worked out okay. The first two periods, I was stupid to change it. that good now? Can you see that? Okay. Okay. So can you see the paper going up and down? Yeah. And now we're gonna do this thing. I think I need this to go a little faster. I gotta tell you, I'm glad I'm videotaping this period where it's totally screwing up. Okay, here it'll catch up. Oh, it's gonna be, oh, there it is, look at that. Oh, isn't that amazing? Don't they kind of match each other? Here, that'll catch up again. Here, watch, wait, there's 180 degrees out of phase. What's catching up? It's catching up? Oh, come on, now they're like totally at the same period. Oh, here we go. You guys okay with that, huh? Well, look at that. One period. Works out great. Here, just a second. Oh, yes. Sometimes it works really well. Come on, baby. Come on, you can do it. Catch up. They are in phase right now. They're in phase. Look at that. That was beautiful. Okay, I gotta go a little faster. Let me do that thing where I started like that. Is that okay? Yes. You good with that? Yeah. Do you believe? Sort of. Oh, don't. That's totally tracks it. It's like the same darn thing. Come on, you guys, sort of. So you good with that? Okay. You guys. Okay, there's another thing I want to show you. It's an actual video where it's not nearly as cool as what I did, but it's probably better. I can actually take this thing down now. This is my last period of having this. Okay, here we go. You ready?
This rotating disc and a weight on a spring will be used to show the similarity between uniform circular motion and simple harmonic motion. A spot on the edge of the disc allows us to see the constant rotational speed of the disc. If we set the weight oscillating in time with the spot on the disc, the weight is always at the same horizontal level as the spot.
Okay, now are you convinced? I would have preferred if they turned that circular thing sideways, and then you would have just seen them going up and down, but whatever. Okay, well. So, let's go ahead and talk now about amplitude. I got to make sure you understand what amplitude is. Alrighty? Let's say I've got my thing, my spring mass system, and it's oscillating between here and there. That is, my spring mass system at its highest point is right there, and then it goes down until it reaches its lowest point, which is right there, and then it goes back up. You guys okay? So my spring mass system is going up and down like that, alrighty? Well, we want to measure its amplitude of oscillation. That is, how much is the distance between where it's at its highest point and where it's at its lowest point. But we do not measure the amplitude or express the amplitude as that big distance there. We actually do this. We actually look at this spring mass system and ask ourselves, okay, where's the equilibrium point? And then we measure our amplitude relative to that equilibrium point. So one definition of amplitude is going to be the maximum excursion from the equilibrium point. That is, here in the middle is the equilibrium point. And your amplitude is going to be measured from the highest point to the equilibrium point. That's your amplitude. And so if I can define amplitude, it is the maximum excursion from equilibrium. So for example, if you go to the beach and you hear on the radio that the waves are 3 to 4 feet, what they're talking about is if you go really far away from shore and you see your waves, you know, a few hundred yards away from shore, then the maximum excursion from equilibrium, the maximum excursion from a completely still water is going to be 3 to 4 feet. That is, this distance from there to there would be 3 to 4 feet, or this distance from there to there would be 3 to 4 feet. That's what they mean by equilibrium. I'm sorry, that's what they mean by amplitude. So consider my daughter, my cute little 8-year-old daughter. She's a little more than 4 feet tall. Does that mean if the radio says 3 to 4 foot waves, I should let her go into the beach completely unsupervised? Okay. Hey, no way, because here's the sand, here's my daughter. The amplitude is 3 feet, but the peak-to-peak distance is 6 to 8 feet, right? Which means when that wave comes over my daughter, and this is the trough and that's the crest of the wave, that is, by the time the wave reaches the beach, we're looking at peak-to-peak value. This is going to be 8 feet or 6 feet, right? I can't let my daughter be unsupervised under those circumstances. You see? So just be aware of the difference between amplitude and peak-to-peak values. So anyway, that's the amplitude of my wave. So now let's talk more about this idea of uniform circular motion being the same as simple harmonic motion. Imagine I have my displacement, my spring mass system, which is just going up and down. This is equilibrium, okay? And it's going up as high as the amplitude A, and going down as low as the amplitude negative A. So my spring mass system is just going up and down. But I want to remind you, you can also think of this as uniform circular motion. You can think of my mass or something traveling around in a circle. So that when my thing that's traveling around in a circle is right there, that would be equivalent to my mass of my spring mass system being there. I am now going to make a mathematical relationship between this point on the circle, the red dot in that video you saw, this point on the circle going round and round, and my spring mass system going up and down. This distance from here to here is its position. Its position at any time. The distance from equilibrium is its position. But I can also say that I've got this radius, which by the way, the radius is A, the amplitude. So that radius is A. And this angle theta is how many radians your little circle is rotated in the time that your spring mass system went down to there. And so I hope you see that there's a relationship between the position of my spring mass system and the position of this dot on the circle. And the relationship would be the length of that segment right there. And that segment has a length of A cosine theta. And that's what x is. So at this particular point in time, x is equal to a cosine theta. But here's the thing, I want to get an expression of x for any time, not just right there, but at any time. And so I'm going to get this expression x of t equaling a times the cosine of, and now I need to express theta in terms of time. Well, we know that x equals vt. We learned that a long time ago when we did kinematics. And then when we did rotational kinematics, we know that the rotational version of displacement is angular displacement, and the rotational version of velocity is angular velocity. So I got theta equals omega t. I don't know why I drew that t so freaky. And so I'm just going to substitute that for theta. And there you go. I get x of t equals a cosine omega t. And so now you see, remember a few days ago when I had the spring mass system going up and down, and I walked across the room and it made a sine wave or a cosine wave? Well, now you see why. We just showed mathematically that the displacement is modeled by a cosine curve. Kind of keeping this in the back of our mind, I want to define frequency, angular frequency, and period for you. First, frequency, which we call by the small letter f. And frequency has the units of cycles per second. But it can also have the units of revolutions per second. So the frequency of oscillation is going to be how many cycles or how many revolutions something does in 1 second. Frequency, number of cycles or revolutions something oscillates. In 1 second. Hey, let's get the frequency of oscillation of this spring mass system. Now the thing is, I have to be aware of what one cycle is. One cycle is, it's at some place and it completes an entire cycle and returns to its original place. So if I'm the type of person who likes to key on the top of its travel, then 1 cycle would be the time for it, or rather 1 cycle is it going from here down to there, back up to there. That'd be 1 cycle. But if you're the type of person who likes to key on the bottom, that's okay. 1 cycle would be from here, up to there, back to there. That's 1 cycle. If you're someone who likes to key on the center of things, as this thing is going down, let's say, then 1 cycle would be for it to go, and that would be 1 cycle. You return to your original point going in the same direction. Okay, well, hey, let's find the frequency of oscillation of this thing. I'm going to count 5 cycles, and I'm going to time it. Reset. Okay. I'm going to do clicky at the top of it, and then I'll count 5 cycles. So here it goes. Just a second. I want to get the rhythm. I'm getting ready, and here we go. Clicky. 1, 2, 3, 4. Clicky. Okay. And so I got 6.6 seconds. So this thing did 5 cycles in 6.6 seconds. I'd like everyone right now to please find me the frequency of oscillation of this spring mass system. So are you guys getting 5 cycles in 6.6 seconds? Which was that, like 0.76? Yes. All right. So that's going to be 0.76 cycles per second. How many people got that as the frequency of oscillation? Okay, beautiful. Now here's the weird thing. There's some dude named Frank Hertz, and he did a bunch of work with microwave radiation and other things that were oscillating. And so humankind decided to honor him by naming the unit of frequency after him. So we don't go 0.76 cycles per second, no siree, we go 0.76 hertz, named after this dude named Frank Hertz. And so we shorten it to HZ. So it's 0.76 hertz. But I just want you to, it's really important to remember that hertz are cycles per second. It is now time to define angular frequency. Which angular frequency is called omega. And the units are radians per second. Now, angular frequency, why would they call angular frequency by the same name as angular velocity? Well, they're different. We think about them differently. But what do they have in common? Say again? Yeah, thank you very much, Robbie. The units, they're both radians per second. And again, you know, it's so funny, this whole demo thing that I've been showing you, I need you to get used to thinking in terms of something up, going up and down, having a attribute of rotation, okay? So look, one cycle from there to there, that's one cycle. That would mean that my circle would have to rotate all the way down and then all the way back up. So my little circle that's tracking this motion, how many revolutions would that circle make? One revolution, which means how many radians? 2 pi. So you guys okay that one cycle is the same as 2 pi radians? It's the same as 2 pi radians because the little circle that's going along with this would do 2 pi radians of rotation. And so that gets us a relationship between angular frequency and normal frequency. If one cycle is the same as 2 pi radians, what if I told you something had a frequency of 1 cycle per second? Then how many radians per second would that be? Yeah, 2 pi. 2 pi radians per second. Okay? So we get our relationship, omega, which is radians per second, just so I can tell Mark. Omega, which is radians per second, is just 2 pi times your normal frequency. That's the relationship. If something is oscillating at 2 cycles per second, then it's oscillating at 4 pi radians per second. So I'd like everyone right now to please get me the omega of my spring mass system. What's the angular frequency of this spring mass system? Hopefully you're doing 2 pi times 0.76. So my omega ends up being, what is that, 4.8? Yeah, 4.8. 4.8 radians per second. 2 pi radians per revolution times 0.76 revolutions per second. Okay, so that's omega, the angular frequency. Finally, we've got period. Let me get this out of the way. Period. And period is a time. It's the most important time there is in talking about oscillating things. And so period gets called capital T for a really important time. And the period is units of seconds. And the period is the amount of time for an oscillating object to complete one cycle. Period equals time to complete one cycle. Or you might want to think of it as the number of seconds per cycle. So that's period. Number of seconds per cycle. Well, what do you notice about the units of period and the units of frequency? What's that? What do you notice about the units of frequency and the units of period? I can't understand. Yeah, thank you. They're reciprocals. Good. Yeah, you flip them, right? And so since their units are reciprocal, since one of them is the number of cycles in 1 second and the other is the number of seconds for one cycle, well, you know, I hope you see that the relationship between period and frequency is going to be that they're reciprocals of each other. That's simple. Period is always the reciprocal of frequency. So for this spring mass system, I'd like you to please find the period. The frequency is 0.76 cycles per second. Yes, sure. Just I hope you guys are getting the reciprocal of that. 0.76 cycles per second. The reciprocal is going to be 1.3 seconds per cycle. Okay, and you know, it's weird, that's the units of period, seconds per cycle, except for some reason, scientists don't say seconds per cycle. They'll say cycles per second for frequency, but they don't say seconds per cycle. Because you know, cycles is a unitless quantity like radians, and so they just go 1.3 seconds. They just forget about the cycle. They go, well, it's understood that it's 1.3 seconds per cycle, so we'll just say the period is 1.3 seconds. Even though it's actually 1.3 seconds per cycle. Okay, well, hey, if you're down with all of that, it's time for you to do one more problem involving amplitude, frequency, angular frequency, and period. Here it comes. Let's say I made a graph of position, and this is in centimeters, the position of a oscillating spring mass system versus time. And it goes like this. Okay, so there's my graph of position versus time of my spring mass system. I'd like you guys to get the following things. Get me the amplitude, the frequency, the angular frequency, and the period. Good luck. You guys done? Yay. Then let's go for it. What's the amplitude? Great. How many people here got 20 centimeters? Yay for each and every one of you. What's the frequency? What's my cycles per second? How many people are getting 0.25? Okay, good. You got 0.3. How did you get 0.3? Oh, no? You know, because this is one complete cycle from there to there. One cycle in 4. That's 1.5 cycles from 0 to 6, but that's not 2 full cycles. Hey, thanks for telling me. Okay, great. So we've got one cycle, and it takes place over the course of 4 seconds. This is my one cycle right there. And so, yeah, 0.25 hertz. Great. So what's my omega? What's my angular frequency? What's that? At 1.6. Did anyone do this? Did anyone just go, hey, 2 pi times 1/4, which gets me pi over 2 radians per second? Did anyone just express it like that? That's fine. Did anyone call it 1.57 or 1.6? That's fine too. And then finally, what you guys get is the period. 4 seconds, yeah. It's going to be the reciprocal of frequency. So it's going to be 1 over 0.25 hertz, which is 4 seconds. Great. All right. Hey, that's amplitude, frequency, angular frequency, and period. There's one last thing we need to talk about, and that's maximum velocity and acceleration. And to do that, we're going to have to do some calculus. So if you're not in calculus, don't worry about this. You know how x of t equals a cosine of omega t? Well, I can take the derivative of both sides of this equation with respect to t. Does anyone remember from calculus? What's the derivative of the position function? Velocity. Yeah, velocity, good for you guys. So I get velocity equals, and the derivative of the cosine is the negative sine, except I have to multiply by the derivative of what's in the parentheses. So I end up with my velocity being negative a omega sine of omega t. But in the textbook, they're not going to ask you to really deal with this equation so much. They're just going to ask what the maximum velocity is. Well, the maximum velocity, you know, sine of omega t, the biggest it can be is 1. So your maximum velocity, your maximum speed is just a omega. And that's it. So they're going to give you problems where they're going to give you amplitude in omega and ask, what's the maximum velocity? And you'll just mindlessly plug into the formula, a omega. How's the maximum velocity a omega? Well, it just comes from this. And the same sort of thing happens with acceleration. If I take the derivative of my velocity equation, I get my acceleration equation, and that ends up being a omega cosine of omega t. But then I have to multiply by the derivative of omega t, which is another omega, pops out. So I've got a of t equals negative a omega squared cosine of omega t, right? And so I want you to see in there, again, the only thing that the book is going to care about is the maximum value. So my maximum acceleration ends up being a omega squared. So they might give you a problem where they tell you the maximum velocity and ask, what's the omega? And you'll just plug into that formula. So here's the last thing. For my spring mass system, well, no, I didn't do that. How about for this guy? For this guy, for this pretend thing, what's the maximum velocity? Yeah, you guys okay with that? 10 pi. It's just going to be a omega, which is 20 centimeters, times omega, which is pi over 2 radians per second. But the weird thing is, radians isn't really a unit. I mean, it's unitless. It's a unit, but it's unitless. So I end up with 10 pi centimeters per second. And so that's the maximum velocity your spring mass system is going to have, which I think is kind of weird because the way we got that was multiplying by angular frequency, even though it's not moving around and around in a circle. But we can still talk about the angular frequency of a spring mass system and use it to find maximum speed. All right. Well, hey, so hope you guys enjoyed it. Hope you're good with the demo. Hope you're good with amplitude, frequency, and frequency theory. Hope you're good with Maxwell Austin solutions.